In the vast, silent reaches of the interstellar medium, where temperature drops to just a few degrees above absolute zero, a whisper of matter begins to stir. Invisible to the human eye, a faint density fluctuation, no more than a seed of dust and gas, drifts within a giant molecular cloud. It is neither bright nor hot. It does not yet shine. And yet, this trembling condensation holds the promise of a star. Gravity, patient and relentless, begins its quiet work. It draws the gas inward, wrapping the fragment tighter with every passing millennium. The cloud core shrinks, compressing under its own weight, growing warmer and denser. What was once a tranquil region of dust now churns with turbulence, magnetized filaments coiling around the collapsing core like skeletal scaffolding of future brilliance. As the gas falls inward, it forms a flattened disk, spinning ever faster due to conservation of angular momentum. At the center of this growing structure lies the protostar, a hidden ember deep within an opaque cocoon. It is not yet a true star, for fusion has not begun, but already it radiates in the infrared, its warmth a silent prelude to what is to come. The dust surrounding it glows faintly, echoing the heat of compression and the friction of infalling matter. Jets of plasma erupt from the poles, slicing through the surrounding cloud like lances of energy. These bipolar outflows help clear away excess material, regulating the mass accretion and shaping the stellar environment. Magnetic fields thread through the forming disk and jets, guiding the newborn star's earliest breaths. The protostar grows heavier, hotter, more luminous. Hidden from view, nuclear pressure builds in its core. There comes a moment, a threshold, when the temperature at the center rises above 10 million Kelvin. Hydrogen nuclei, once content to drift alone, begin to fuse. With that ignition, the protostar crosses a boundary into stellar life. It becomes a main sequence star, no longer fed solely by collapse, but by the energy of its own reactions. The cocoon begins to thin. Light, once imprisoned, escapes. From darkness, from cold, from disorder, emerges the fire of a star. The dust that once veiled the light becomes the very ingredient of planetary systems, of moons, of oceans, and of life. Every heartbeat, every atom of calcium in a bone or iron in blood, was forged in a process that began with that quiet collapse. Before the brilliance, there was silence. Before fusion, there was falling. Before light, there was only shadow. Observations of protostellar evolution have been revolutionized by infrared and submillimeter astronomy. Telescopes like the James Webb Space Telescope and ALMA peer into the thick veils of dust that obscure these early phases, revealing disks, jets, and magnetic turbulence that shape the path to stardom. These instruments capture light that has traveled for thousands of years, emitted not by nuclear fusion, but by the friction of collapse and the glow of accretion shocks. Protostars are classified by their spectral energy distributions into stages, class 0, 1, 2, and 3, each marking a distinct chapter in the transformation from dense core to luminous star. In the earliest stage, class 0, the object is entirely enshrouded in its envelope, with more mass in the surrounding cloud than in the protostar itself. As it accretes matter and grows, it moves into class 1, where the central source dominates and the envelope begins to dissipate. Class 2 marks the emergence of a visible star with a prominent disk, the birthplace of future planets. Finally, class 3 denotes a star that has largely shed its disk, now entering maturity. Magnetohydrodynamic simulations of protostellar collapse provide deep insights into the complex interplay of gravity, rotation, pressure, and magnetic fields. These models show that without angular momentum loss, mediated by magnetic braking or jet-driven outflows, a protostar could not efficiently accrete material. Magnetic reconnection events within the disk may also trigger bursts of accretion, a phenomenon observed in so-called Fu-Orioni stars, whose brightness can increase by a factor of 100 over a few months. Chemical evolution during these early stages is equally profound. As dust grains migrate inward, they undergo heating, triggering the release of ices and complex organic molecules. These molecules, formaldehyde, methanol, acetylene, and even prebiotic precursors, can seed the future planetary system. Thus, even before the star begins fusion, the conditions for chemistry and ultimately biology are quietly taking shape. In binary systems, the story grows even more intricate. Interactions between protostars, their disks, and shared envelopes can lead to mass transfer, spiraling dynamics, and the eventual formation of tightly bound pairs or even stellar mergers. These processes not only affect the stars themselves, but can trigger the formation of massive planets or brown dwarfs through gravitational fragmentation of the disk. The birth rate of stars, or star formation rate, is a key parameter in galactic evolution. Protostellar populations in nebulae like Orion or Perseus serve as cosmic laboratories, where thousands of forming stars at various stages can be observed simultaneously. These studies inform models of galaxy growth, stellar feedback, and even the cosmic cycle of matter, from diffuse gas to stellar cores to supernovae and back again. The physics of protostellar accretion disks remains a frontier of astrophysical research. These rotating structures, composed of gas and dust, transport angular momentum outward while funneling mass inward toward the growing star. The primary mechanisms driving this transport, magnetorotational instability, MRI, gravitational instabilities, and disk winds, are actively studied using high-resolution numerical simulations and multi-wavelength observations. MRI, in particular, relies on the presence of weak magnetic fields to induce turbulence, allowing angular momentum to be redistributed efficiently within the disk. Observations with ALMA have revealed detailed substructures in many young disks, such as concentric rings, gaps, and spiral arms. These features may indicate early planet formation or interactions with stellar companions. The discovery of dust traps, regions where particles concentrate due to pressure gradients, supports models in which millimeter-sized grains aggregate into planetesimals even before the star reaches the main sequence. Thus, the architecture of planetary systems may be established while the star itself is still in its embryonic phase. Isotopic studies of meteoritic material in our own solar system suggest that the Sun's protostellar disk was chemically and thermally heterogeneous. Short-lived radionuclides like aluminum-26, likely injected by a nearby supernova or massive star wind, provide evidence that the early solar system formed in a rich stellar nursery, not in isolation. This environment may have influenced the distribution of volatiles and organics that later shaped Earth's atmosphere and biosphere. Gravitational interactions between protostars and their surrounding cloud cores also play a decisive role. Recent simulations show that turbulence in molecular clouds can induce fragmentation, leading to clustered star formation. These fragments may compete for gas, influencing the mass distribution of newborn stars, known as the initial mass function, IMF. Understanding the IMF is crucial for modeling galactic luminosity, stellar evolution, and the chemical enrichment of the interstellar medium. Meanwhile, the feedback from young protostars is far from passive. Bipolar jets and wide-angle winds inject momentum and energy into the cloud, carving out cavities and potentially triggering or suppressing further collapse in neighboring regions. Observations with instruments like SOFIA and Herschel have revealed complex shock structures and ionized flows extending light-years from their source. These outflows regulate both the growth of the protostar and the structure of its stellar nursery. On cosmic timescales, protostellar formation contributes to the grand feedback loop of the universe. Stars born in dense clouds enrich their surroundings through stellar winds, radiation, and eventual supernova explosions, seeding the next generation of stars with heavier elements. The cycle of collapse and ignition, of darkness becoming light, is not just a physical process but a cosmic rhythm, threading together the past and future of galaxies. At the scale of galaxies, protostellar formation is tightly linked to the dynamics of spiral arms, bars, and gas inflows. In spiral galaxies like the Milky Way, density waves compress interstellar gas along the arms, creating the ideal conditions for molecular cloud collapse. These spiral shocks slow down the gas relative to the stars, allowing regions of higher density to build up. Inside these pockets, gravity eventually overcomes pressure and turbulence, giving birth to protostars en masse in what are known as stellar nurseries. Galactic bars, too, can funnel gas toward the central regions of galaxies, boosting the star formation rate and sometimes triggering nuclear starbursts. These intense periods of star birth can form thousands of protostars per year in a compact region, as seen in starburst galaxies like M82. There, the interstellar medium becomes a chaotic environment filled with shock waves, strong magnetic fields, and overlapping feedback from jets and winds, producing extreme conditions that test the limits of current theoretical models. In the early universe, the very first protostars, known as population 3 stars, formed under radically different conditions. Lacking metals, elements heavier than helium, these primordial gas clouds could not cool efficiently, leading to the formation of stars that were likely far more massive than those born today, some exceeding hundreds of solar masses. These colossal stars burned quickly and died violently, enriching their surroundings with the first heavy elements and setting the stage for the next generations of protostars. Modern cosmology aims to model these first luminous objects, using simulations that combine hydrodynamics, chemistry, radiation transfer, and gravity in 3 dimensions. These simulations suggest that protostellar disks existed even in the first billion years of cosmic time, and that fragmentation in these early disks may have produced binary or multiple systems, similar to what we see in today's star-forming regions. Observations by JWST are beginning to reveal galaxies at redshifts beyond 10, where early protostellar populations may still be faintly detectable. Even now, many of the deepest questions remain. What sets the mass of a star at birth? Why do some regions of galaxies form stars prolifically, while others remain quiescent? What mechanisms determine whether a collapsing gas core becomes a brown dwarf, a star, or an object on the edge of both? Answering these questions requires not just observation, but theoretical insight, connecting physical laws from plasma physics and thermodynamics to the large-scale structure of the cosmos. In the end, the study of protostars is more than an investigation into beginnings. It is a search for continuity between the simplest atomic clouds and the complex architectures of planetary systems. From a single dust grain to a nuclear furnace, from gravitational collapse to the ignition of light, every step in the life of a protostar echoes in the broader story of cosmic evolution. High-mass protostars, those destined to become stars more than 8 times the mass of the Sun, present a distinct challenge to both observation and theory. Unlike their low-mass counterparts, they evolve rapidly, reaching the main sequence while still accreting material. Their powerful radiation fields, intense stellar winds, and strong UV output begin to ionize and disrupt their surroundings even before accretion ends. This interplay between continued growth and self-destruction makes massive star formation a finely balanced and turbulent process. Observationally, massive protostars are rare and tend to form in distant, obscured regions of the galaxy, buried deep within dense cores of giant molecular clouds. Instruments like ALMA and the Very Large Array allow astronomers to probe these regions at radio and submillimeter wavelengths, revealing clustered star formation, complex filamentary structures, and rapidly rotating disks around massive cores. In many cases, these disks are unstable, fragmenting under their own gravity and possibly giving rise to secondary stars or massive planets. Radiation pressure from the forming star poses a fundamental limit to continued accretion. For a time, it was thought that beyond a certain mass, perhaps 20 or 30 solar masses, radiation would prevent any further inflow of gas. However, models now suggest that accretion can continue through dense equatorial disks, where material is shielded from the star's harshest radiation. Moreover, collimated outflows and jets may carve low-density escape channels along the poles, allowing radiation to escape without halting infall entirely. These theoretical insights are increasingly supported by observation. Hypercompact H2 regions, Tiny zones of ionized gas enveloping the youngest massive stars are detected near strong millimeter continuum sources, indicating that accretion and ionization coexist. Maser emission from molecules like water and methanol also trace shocked regions and outflows, revealing complex kinematics around massive protostars. Feedback from high-mass protostars dramatically reshapes their environments. As the protostar grows, it creates a bubble of ionized gas, sweeping up surrounding material into a dense shell. Over time, this shell may become gravitationally unstable, collapsing to form a new generation of stars, a process known as triggered star formation. In this way, massive stars not only disrupt but also catalyze the next wave of stellar birth, propagating a chain reaction of creation across entire molecular complexes. Massive protostars are also key players in galactic evolution. Their short but intense lives end in supernova explosions, injecting energy, momentum, and heavy elements into the interstellar medium. The resulting shock waves can compress nearby gas, mix and distribute metals, and influence the dynamics of the surrounding spiral arms. The seeds of new planetary systems, rich in carbon, oxygen, silicon, and iron, owe their origin to such explosive feedback. Modern research now integrates data from multiple wavelengths and physical regimes, combining radio maps of cold gas, infrared views of warm dust, X-ray emission from stellar shocks, and optical spectroscopy of outflows. Astronomers are building a holistic picture of protostellar evolution. Machine learning and AI-based data analysis are also entering the field, helping classify protostellar objects across vast datasets and identify patterns that elude traditional methods. In every observation of a protostar, whether it is a faint glimmer in the Orion Nebula or a massive core on the brink of collapse in a distant spiral arm, we are witnessing a chapter in the great story of stellar genesis. These are not just stars in the making. They are engines of galactic change, factories of elements, and cradles for future worlds. Their birth is a symphony of gravity, turbulence, radiation, and time, a process still ongoing across the universe, echoing the same ancient rhythm that once brought light to our own sky. Protostellar disks, the swirling structures of gas and dust encircling young stars, are not merely passive bystanders. They are active workshops, planetary laboratories where future worlds take shape. Within these dense, rotating disks, grains of cosmic dust slowly aggregate, forming pebbles, rocks, and eventually planetesimals, the foundational building blocks of planets, moons, asteroids, and comets. Recent observations have dramatically changed our understanding of the timescale and complexity of planet formation. Images from ALMA have captured intricate patterns in these disks, including clear, ring-shaped gaps, spiral arms, and asymmetric dust concentrations. These structures often signal the presence of young planets, orbiting protostars that have not yet fully ignited fusion. Thus, planetary birth may overlap with stellar birth, underscoring how deeply intertwined the two processes truly are. One mechanism underlying these patterns is gravitational interaction. Forming planets carve out gaps by gravitationally clearing orbital paths, redirecting gas flows, and creating local pressure traps. In these traps, dust grains gather and grow more rapidly, potentially catalyzing rapid planetesimal formation. Numerical simulations indicate that these early processes can occur swiftly, perhaps within only a few 100,000 years after protostellar collapse begins, challenging earlier notions of slower sequential growth. Chemistry within protostellar disks also profoundly influences the characteristics of future planetary systems. Variations in temperature and radiation lead to chemical stratification. Volatile substances, such as water and ammonia, condense in colder outer regions, while silicate minerals and metals remain dominant near the warmer inner disk. These compositional gradients eventually translate into different planet types: rocky, terrestrial planets close in, and gas-rich or icy worlds farther out. This framework provides insights into our own solar system's architecture. Studies of meteorites, comets, and primitive asteroids reveal a record of chemical gradients preserved from the protostellar disk era. The distribution of water and organic molecules, essential ingredients for life, was likely established even before Earth formed. Thus, habitability, the potential for life, may trace its roots back to the protostellar environment itself. A particularly intriguing field of research involves analyzing isotopic signatures found in meteorites, which provide clues about the earliest phases of solar system evolution. Short-lived radionuclides and isotopic anomalies, such as oxygen and nitrogen isotope ratios, suggest complex transport processes within the early solar nebula. High-temperature grains forged near the young sun were mixed with icy materials drifting inward from outer regions, creating the heterogeneous environment from which our planets emerged. Advanced modeling now explores the dynamic interplay between magnetic fields, gas dynamics, and dust evolution within disks. Simulations demonstrate how turbulence, driven by magnetohydrodynamic instabilities, influences grain growth, sedimentation, and radial drift. These processes strongly shape where, when, and how planets form. Such models not only reproduce observed disk structures but also predict the conditions necessary for Earth-like planets versus gas giants. Observations of exoplanetary systems further deepen our understanding. The surprising diversity of planet architectures, hot Jupiters, super-Earths, tightly packed planetary systems, challenges simple theories. By tracing these planets' origins back to protostellar disks, astronomers seek universal patterns underlying planet formation, hoping to understand whether the solar system is typical or exceptional. Protostellar disks also serve as natural laboratories for testing theories of physics and chemistry under extreme conditions. Cosmic ray irradiation, ultraviolet exposure, shocks from disk winds and jets, all these influence chemical reactions that generate complex molecules, potentially including precursors to life. Recent detections of amino acid precursors in protostellar environments strengthen the connection between stellar nurseries and biological origins. At its core, the formation of planets is not a separate event, but a natural outcome of the star-forming process. Every planetary system, including our own, began hidden within a protostellar disk, quietly assembling while the central star itself was still awakening. By exploring these cosmic birthplaces, we trace not just our astronomical origins, but also the deeper question of life's place in the universe. The delicate link between protostellar environments and the emergence of conditions necessary for life has grown into a central theme of contemporary astrobiological research. Within protostellar disks, astronomers have now identified a remarkable diversity of organic molecules, from simple hydrocarbons and alcohols to complex prebiotic molecules, such as formamide, glycolaldehyde, and methyl isocyanate, molecular building blocks essential for the chemistry of life. Recent spectral studies from ALMA and JWST have confirmed that protostellar disks around young, sun-like stars contain abundant reservoirs of water ice, ammonia, carbon monoxide, and organic-rich compounds. These molecules are embedded in dust grains, forming icy mantles that serve as protective vessels for chemical reactions driven by UV radiation, cosmic rays, and thermal shocks. Over time, grains migrate inward toward warmer regions, triggering sublimation that enriches the disk's gas phase chemistry. Such chemical enrichment processes strongly suggest a universal pathway linking star formation directly to prebiotic chemistry. Laboratory experiments complement these astronomical observations. By replicating conditions found in protostellar disks, cold vacuum chambers irradiated by ultraviolet photons and energetic particles, scientists have demonstrated that surprisingly complex organic molecules spontaneously form on icy dust grain analogs. Such molecules include sugars, amino acids, nucleobase precursors, and amphiphilic compounds that could catalyze self-assembly and membrane formation, crucial steps towards cellular life. Thus, star formation environments inherently possess the ingredients required for life's molecular foundations, waiting only for the right planetary context to express their full potential. The migration and redistribution of these materials within disks further shape planetary habitability. Dynamical processes, such as radial drift and planet migration, redistribute volatile-rich materials across wide orbital ranges. This can result in rocky planets receiving deliveries of water and organics long after their initial formation. Recent isotopic analyses of Earth's water and volatile elements strongly suggest such processes occurred early in the solar system's history, likely seeded by protostellar disk dynamics and turbulent mixing. Protostellar outflows and jets, once viewed merely as mass loss mechanisms, are now understood to influence disk chemistry profoundly. The shocks they produce drive chemical reactions, forming complex organic molecules and inducing isotopic fractionation. These enriched molecular clouds subsequently re-enter protostellar disks, continually refreshing chemical complexity. Such feedback loops indicate that stellar birth and chemical evolution operate in an intricate dance, each influencing the other across astronomical timescales. At a larger scale, comparative studies of exoplanetary systems reveal the wide diversity in planetary composition, atmospheres, and orbital dynamics, directly shaped by the initial protostellar environment. Hot Jupiters, water-rich sub-Neptunes, and terrestrial worlds orbiting in compact, resonant systems illustrate outcomes determined by initial disk conditions. Through this comparative lens, protostellar research directly informs our understanding of the probability and diversity of habitable worlds across the galaxy. Astrochemical modeling efforts increasingly integrate detailed chemical networks with sophisticated fluid dynamic simulations, enabling predictions of how and where complex molecules form. These predictive tools not only interpret current observations but guide future explorations. For instance, they help target observations of molecules considered critical markers for prebiotic chemistry in distant, young planetary systems. Such observations are within reach of JWST and next-generation telescopes, transforming theoretical predictions into empirical discoveries. Ultimately, protostellar science holds profound philosophical implications. By tracing our biochemical origins back to these stellar nurseries, we are led to the realization that life's essential ingredients were not unique or exceptional. They were common, dispersed across countless protostellar disks throughout cosmic history. The profound implication is clear. Life's potential is woven into the fundamental processes of star and planet formation itself. The intricate relationship between protostellar environments and life's biochemical precursors deepens when considering cosmic radiation and stellar activity. Young protostars often exhibit intense magnetic activity, producing energetic flares and ultraviolet bursts that significantly alter the chemistry of surrounding disk material. While at first glance hostile, these high-energy events actually catalyze critical molecular reactions that might otherwise proceed too slowly to form biologically relevant molecules. Such stellar irradiation thus paradoxically enhances chemical complexity, contributing directly to the formation of prebiotic molecular reservoirs. One particularly intriguing phenomenon is the impact of cosmic rays, highly energetic particles originating from supernova explosions and energetic stellar winds that continuously bombard protostellar disks. Cosmic rays penetrate deeply into dense molecular clouds and circumstellar disks, breaking molecular bonds and producing a cascade of reactive radicals and ions. These species rapidly recombine, giving rise to complex organic molecules such as amino acids, aldehydes, and nitriles. Laboratory experiments confirm that cosmic ray analogs can generate amino acids in icy analogs of protostellar grains, implying cosmic rays might have directly contributed to life's initial chemical toolkit. Protostellar magnetic fields also profoundly shape the early planetary environment. Observational studies using polarization-sensitive instruments reveal that dust grains within disks often align along magnetic field lines, providing clear observational signatures of these fields. Magnetically driven turbulence regulates disk accretion rates and dust grain dynamics, influencing planetesimal formation efficiency and chemical transport. Magnetic reconnection events can trigger sudden bursts of brightness and energetic particle acceleration, stimulating complex chemical reactions deep within the disk, ultimately enriching the planetary building blocks. Additionally, observations have shown that protostellar outflows entrain not only gas and dust, but also complex molecules, ejecting them far beyond the protostar's immediate environment. This molecular transport effectively seeds nearby star-forming regions, propagating chemically enriched material through stellar nurseries and potentially enhancing prebiotic chemistry in neighboring systems. The concept of protostellar ecosystems thus emerges. Individual protostars may chemically communicate across parsec-scale distances, collectively contributing to a galactic-scale chemical evolution. Emerging theoretical models now explore the potential connection between protostellar chemistry and planetary atmospheres. The chemical fingerprints acquired during a planet's early formation stages might persist within its atmosphere and interior throughout geological time. Consequently, protostellar disk chemistry could help explain the variety observed among exoplanetary atmospheres, some rich in carbon dioxide or methane, others dominated by hydrogen, nitrogen, or water vapor. These atmospheres ultimately determine planetary climate stability, habitability, and the likelihood of biological emergence. The search for biosignatures in exoplanetary systems increasingly intersects with protostellar research. Astronomers are developing observational strategies to trace molecules considered vital precursors to life directly within protostellar disks. Detecting such molecules across diverse protostellar systems could provide a statistical framework for understanding life's prevalence in the galaxy, thus anchoring astrobiological hypotheses firmly within empirical science. At an even broader level, protostellar research contributes insights into one of cosmology's fundamental questions. How common is life in the universe? The presence of abundant prebiotic compounds across protostellar environments implies that the raw ingredients for life exist everywhere star formation occurs. If the molecular precursors for life are ubiquitous, the formation of habitable worlds and potentially life itself might be routine rather than rare events in cosmic history. Future telescopes, including ESA's Ariel mission, NASA's Origin Space Telescope, and the next-generation ground-based Extremely Large Telescopes, ELTs, will probe protostellar disks at unprecedented resolution and sensitivity. These observatories promise to reveal chemical and physical processes with exquisite detail, allowing astronomers to directly test and refine models of planet formation, chemical complexity, and potential habitability. This new era will not only sharpen our understanding of star and planet formation, but could bring humanity significantly closer to answering the enduring question of whether life is a cosmic inevitability. Advances in computational astrophysics now enable astronomers to simulate protostellar and planet-forming environments with remarkable detail, encompassing scales from microscopic dust grains to entire stellar clusters. These simulations, informed by observations, integrate gravity, magnetohydrodynamics, radiation transfer, and complex astrochemical reactions to paint realistic pictures of early stellar nurseries. High-performance supercomputers generate virtual protostellar disks and clusters, allowing scientists to probe questions unreachable by current observational technology, such as how quickly Earth-like planets form, or how common prebiotic chemistry is across the universe. Recent simulations reveal how dust grains within disks undergo intricate growth pathways. Dust evolution begins with tiny interstellar particles, micrometers in size, which collide gently in low-velocity regimes, sticking together electrostatically to form porous aggregates. As these aggregates drift inward, they encounter increasingly turbulent regions, experiencing collisions that either promote growth or lead to fragmentation. This dynamic equilibrium determines the availability of planet-building material and shapes planetesimal formation processes, thus directly influencing the diversity and distribution of future planetary systems. One particularly compelling scientific frontier involves the direct imaging of protostellar disks in polarized infrared and millimeter wavelengths. Polarization observations reveal grain-size distributions, magnetic field orientations, and scattering properties, thus providing crucial insights into disk structure and evolution. For instance, recent polarimetric imaging from ALMA and Subaru telescopes has shown that young protostellar disks exhibit polarization patterns that indicate grain alignment by radiation or magnetic fields, offering tangible evidence of the interplay between magnetic fields and planetary formation. The discovery of protoplanetary disks in extreme environments, such as around protostars near massive black holes or within crowded star clusters, further expands our understanding of planet formation processes. Studies suggest that disks near supermassive black holes or within dense stellar clusters experience dramatically different irradiation levels, gravitational interactions, and dynamical perturbations compared to more isolated environments like our sun's birthplace. Remarkably, planets formed under these exotic conditions might differ greatly in composition, stability, and potential habitability. Protostellar populations themselves also inform broader astrophysical models. The distribution of stellar masses, called the initial mass function (IMF), is fundamental for understanding galaxy evolution, stellar population synthesis, and even the cosmic history of element production. Recent observational studies hint that the IMF might vary with environment, density, and metallicity of the star-forming clouds, suggesting star formation is more context-dependent than previously recognized. Thus, insights from detailed protostellar observations not only illuminate stellar and planetary origins, but also have implications for cosmological theories of galaxy assembly. Additionally, protostars serve as testing grounds for fundamental physics. The interplay of gravity, magnetism, and turbulence within disks provides natural laboratories for studying plasma instabilities, turbulence scaling laws, and magnetized fluid dynamics. These physical insights have cross-disciplinary impacts, influencing fields such as fusion research, atmospheric physics, and even Earth's oceanography, where turbulence and magnetic fields play similar roles. Recent astrobiological hypotheses also explore whether protostellar disks themselves might serve as transient habitats. Although life as we know it would struggle to develop in such extreme, radiation-rich environments, some researchers speculate that complex, self-organizing chemical systems, precursors to life, could temporarily form and exist within sheltered pockets in disk interiors. Studying these hypothetical transient chemical ecosystems challenges our notions of habitability and offers novel perspectives on the origins of life, suggesting that biological precursors might arise long before planets solidify and stabilize. The evolution of protostellar clusters introduces another fascinating research angle. Stars rarely form in isolation. Instead, they typically emerge within clusters containing dozens to thousands of protostars. Within these crowded environments, gravitational interactions dynamically sculpt planetary systems, eject stars, and redistribute planetary building material. Cluster dynamics influence planet survival rates, orbital architectures, and the frequency of rogue planets, worlds that wander freely through interstellar space without a host star. Understanding these phenomena sheds light on the diversity and stability of planetary systems throughout the galaxy. Ultimately, modern protostellar science fuses observational astronomy, theoretical physics, chemistry, and astrobiology into a coherent narrative. As telescopes continue to sharpen our view and computational models grow ever more sophisticated, humanity moves closer to grasping the profound connections that bind stellar birth, planetary genesis, chemical complexity, and the emergence of life itself. Protostars remind us that our existence is not a mere cosmic accident, but rather the elegant outcome of universal physical processes, patiently unfolding across billions of years in clouds of interstellar dust and gas. Another rapidly developing area in protostellar research involves the radiative feedback from young stars and its influence on both disk evolution and the broader star-forming environment. As protostars contract and approach the main sequence, they emit increasing levels of ultraviolet, UV, and X-ray radiation. These high-energy photons interact with the disk material and surrounding molecular cloud, heating the gas, ionizing atoms, and driving photochemical reactions. This radiation can photoevaporate the outer layers of disks, gradually dispersing gas and limiting the time available for giant planet formation. Observations from the Chandra X-ray Observatory and XMM Newton have revealed intense X-ray flaring activity in many T-Tauri stars, young, still accreting solar analogs. These flares are thought to arise from powerful magnetic reconnection events and contribute significantly to disk ionization. Enhanced ionization boosts the coupling between magnetic fields and disk material, facilitating magnetorotational instability and turbulence, which are essential for angular momentum transport and sustained accretion. However, strong radiation also accelerates the chemical evolution of the disk surface, affecting the retention of volatile compounds like water and organics, with long-term implications for planetary atmospheres and potential biospheres. In rich stellar clusters, external feedback from massive O-type stars becomes dominant. These stars produce intense UV radiation fields that can erode nearby protoplanetary disks through external photoevaporation. The Orion Nebula, for example, hosts dozens of such irradiated disks, known as proplyds. Imaging from the Hubble Space Telescope has captured these fragile systems surrounded by ionized gas streamers, visibly eroded by their environment. Despite this harsh treatment, many of these disks still retain enough mass to form planets, highlighting the resilience of planet-forming environments even in extreme conditions. Another exciting frontier lies in disk substructures and planet formation diagnostics. ALMA has provided revolutionary high-resolution images of disks like HL Tau, TW Hydri, and AS209, revealing concentric rings, spiral arms, asymmetries, and shadows. These features suggest the presence of embedded planets or instabilities within the disk. The morphology of these structures allows astronomers to estimate the masses and locations of unseen protoplanets, offering a window into the earliest stages of planetary system assembly, while planets are still forming within the dusty cradle of their protostar. Complementary to ALMA, JWST now explores the infrared spectral fingerprints of ices and organics in protostellar disks. Its exquisite sensitivity enables the detection of frozen water, methane, carbon dioxide, and complex carbon-bearing molecules across the disk midplane, the potential feeding zones of terrestrial planets. Spectral maps also reveal temperature gradients and chemical transitions, showing where ice lines or snow lines occur, boundaries where volatiles condense from gas to solid. These lines define zones where different types of planets form and where volatile delivery to inner, rocky planets can occur. Meanwhile, isotopic fractionation studies offer a new diagnostic for early disk chemistry. Ratios such as D/H, deuterium to hydrogen, or superscript 1n/superscript 1n, nitrogen isotopes, vary depending on the physical and chemical conditions in which ice is formed. Comparing these ratios across different protostellar disks, meteorites, and cometary materials allows researchers to trace the evolutionary history of the solar system's own disk and compare it to planetary systems forming today. On the theoretical side, increasingly sophisticated simulations now couple dust dynamics and gas thermochemistry in evolving disks. These models track the radial drift of grains, the formation of pressure bumps, and the coagulation of particles into planetesimals, all while accounting for the chemistry of evolving ices and gases. By matching these simulations with observations, astronomers can test scenarios of planet formation, how Earth-sized rocky worlds or gas giants like Jupiter and Saturn emerge under different disk conditions. Finally, research into protostellar multiplicity reveals that a significant fraction of stars form not alone, but in binary or multiple systems. The gravitational dynamics of these systems can truncate disks, induce eccentric or warped structures, and dramatically alter the pathways of planet formation. In some cases, misaligned disks or inclined binaries may give rise to exotic systems with tilted planets or circumbinary configurations. Understanding how protostars evolve in these complex gravitational settings is crucial for interpreting the vast diversity of exoplanetary architectures now being discovered. Among the most compelling areas in the study of protostellar evolution is the transition from protostar to pre-main sequence (PMS) star, a phase that marks the shift from a heavily accreting, deeply embedded object to a fully revealed young star with a clearing circumstellar disk. This evolutionary milestone is critical for setting the final stellar mass, the disk's remaining lifetime, and the architecture of the eventual planetary system. As accretion from the envelope slows and the infall rate drops, the protostar enters what is observationally classified as the Class II phase. At this point, the star is visible at optical and near-infrared wavelengths, and its spectrum is dominated by photospheric emission rather than accretion luminosity. Yet, even as the star appears more stable, complex processes continue. Magnetospheric accretion, chromospheric activity, and episodic outbursts all define this transitional period. One of the most intriguing phenomena during the pre-main sequence phase is the occurrence of episodic accretion events, as seen in Fu Orionis and EX Lupi stars. These young stars undergo dramatic increases in brightness, sometimes by over 5 magnitudes, triggered by a sudden surge in disk accretion. These bursts can last for years or even decades, and their origin is still under active investigation. Possible triggers include disk gravitational instabilities, thermal viscous instabilities, or the migration of clumps within the disk toward the star. Such events may be crucial in regulating stellar mass growth and influencing disk chemistry, potentially resetting the thermal and chemical environment for planet formation. Simultaneously, disk winds and photoevaporative flows begin to play a dominant role in dispersing the circumstellar disk. Observations show that as accretion wanes, ionizing radiation from the central star, and sometimes external sources, heats the upper disk layers, launching a slow but persistent wind that removes mass from the system. Disk clearing progresses from the inside out, often leaving behind transitional disks with inner holes or gaps. These structures are particularly fascinating, as they may either indicate disk dispersal in progress or the presence of young, embedded planets that are dynamically carving the material. Studies of transitional disks have become a vital probe of planet-disk interactions. ALMA observations frequently reveal multiple rings and gaps, which, in conjunction with hydrodynamical simulations, provide indirect evidence for forming planets. These young systems offer a rare snapshot of planetary assembly and migration in action. Notably, the presence of asymmetries or vortices within transitional disks hints at the trapping of dust and gas, promoting rapid core growth. A possible solution to the timescale problem of forming gas giants before the gas dissipates. The final dissipation of the protoplanetary disk typically occurs over timescales of 3 to 10 million years, although variation exists depending on stellar mass and environment. Once the disk is gone, the star becomes a Class III object or weak-line T-Tauri star, in the case of solar-type stars, now largely isolated from its formation envelope and disk. At this stage, the star continues to contract along the Hayashi track for low-mass stars, or Henny track for intermediate-mass stars, radiating away gravitational energy until hydrostatic and thermal equilibrium are achieved, marking its arrival on the main sequence. Meanwhile, any planets that formed must stabilize their orbits in a disk-free environment, often undergoing dynamical rearrangements. The architecture of the mature planetary system is, in part, a fossil record of the disk structure, the migration history of planets, and the mass accretion history of the host star. Research into the end stages of protostellar evolution also overlaps with studies of stellar angular momentum evolution. Young stars are born rotating rapidly, but disk locking and magnetically driven winds efficiently remove angular momentum, preventing the stars from spinning apart. This interplay between magnetic braking, accretion, and contraction helps define the rotational velocity distribution observed in young open clusters, a key constraint for stellar evolution models. Crucially, the chemical memory of the protostellar phase may persist in planetary compositions. Studies of primitive meteorites, cometary ices, and interplanetary dust particles suggest that some materials accreted onto planets preserve isotopic and molecular signatures inherited from the early disk and envelope. These cosmochemical fingerprints provide a tangible link between present-day planetary bodies and the physics and chemistry of their protostellar origins. In summary, the final stages of protostellar evolution are not merely a tapering off of activity but a critical window in which mass, chemistry, angular momentum, and planetary architecture are finalized. The complex orchestration of accretion, outflow, radiation, and dynamical clearing defines the transition from a chaotic molecular collapse to the ordered structure of a planetary system. The journey from a silent cloud of dust to a luminous star with a retinue of planets is one of the most intricate and awe-inspiring processes in the cosmos. It is a saga of collapse and ignition, of chaos shaped by physics into coherence, of molecules organizing into worlds. From the first whisper of gravity in a dark molecular cloud to the final clearing of the protoplanetary disk, the protostellar phase encapsulates the fundamental forces that give rise to stars, planets, and the potential for life. In every protostar lies the echo of creation, a balance between destruction and formation, between radiation and accretion, between turbulence and order. It is here, in these hidden stellar cradles, that the architecture of future planetary systems is forged, where organic chemistry awakens, and where the seeds of habitable worlds are sown. As telescopes grow sharper and simulations grow deeper, humanity stands at the edge of a profound realization. The processes that gave birth to our Sun and Earth are neither unique nor rare. They are universal, unfolding across the galaxy and beyond. To study protostars is not merely to understand stellar evolution. It is to trace the blueprint of existence itself, to glimpse the quiet forges where matter becomes light, and where the long story of life may begin. And so, in the darkness of collapsing clouds, lit faintly by the glow of forming stars, we find the first sparks of cosmic destiny. For every protostar is a promise, not just of light, but of worlds, of chemistry, of memory, and perhaps, in time, of consciousness.